So, in the last lecture we were getting down to the business of solving the equations that we had derived, and I had shown you that you do get non-trivial solutions for the pressure field even in the absence of flow. It was hydrostatics. The pressure in general is non-zero simply because you could have body forces acting. The next simplest case is a unidirectional flow, where the flow is only along one direction, and in general the gradients are only along the other direction. Let us look at how these arise. The simplest case is the flow in a channel. So, let us take this as the x direction, this as the y direction. Okay. Consider this as a two-dimensional channel which is effectively infinite in the third dimension. So, you should think of this as a slot, okay, which is effectively infinite in the third dimension, and across the two ends of the slot there is some pressure difference that is applied, due to which there is fluid flow in this channel. And now the velocity is only in the x direction, and because you are imposing zero velocity boundary conditions at the two walls, there is a gradient in the y direction. So, let us first try to write down the complete momentum and mass conservation, Navier-Stokes mass and momentum conservation equations for this particular case. Okay. So, in this case the velocity field, I am sorry, the mass conservation equations, del dot u is equal to 0, which if I write it out in these two dimensions, I will neglect variations in the third dimension for simplicity. You could write it easily with all three dimensions as well. Okay. So, this just becomes equal to partial u x by partial x plus partial u y by partial y is equal to 0. The second is the momentum conservation equations. These are now vector equations. So, rho times partial u I by partial t plus u j. Let us neglect the body forces for the present. Okay. You will assume there is no gravity here. So, these are now two equations for the x and y directions. The index I takes values both x and y. Okay. So, you will get rho times partial u x by partial t plus u j partial u I by partial x j. There is a summation over j. That means that you have to add up values for j is equal to x and j is equal to y. Okay. So, this becomes u x partial u x by partial x plus u y partial u x by partial y. I is x in this case. So, I just get minus partial p by partial x plus mu into partial square u x by partial x square, Laplacian of u x. So, this becomes partial square u x by partial y square. So, that is a complete momentum conservation equation in the x direction. Similar equation can be written for the y direction. Okay. So, rho times partial u y by partial t plus u x partial u y. There is the complete momentum conservation equation in the y direction. Now, for this two-dimensional coordinate system, if the flow is unidirectional, okay, if the flow is unidirectional, that means that u y is equal to 0, flows only in the x direction. So, if u y is equal to 0 and flows only in the x direction, that means that in this equation, as you can see, okay, in the y momentum conservation equation, each term has u y in it. Okay. Each term has u y in it. That means that all of those terms are 0. Therefore, the momentum conservation equation in the y direction just reduces to minus partial p by partial y is equal to 0. No dependence of pressure on the cross stream direction, okay, partial p by partial y is equal to 0. There is also an implication for the mass conservation equation. As you can see here, if u y is equal to 0, this term is equal to 0. That means that partial u x by partial x is also equal to 0. That means that for this unidirectional flow, just from the mass conservation condition alone, you cannot have a variation of the x velocity along the x direction. The x velocity is independent of the downstream direction, whereas partial u x by partial x is equal to 0. Okay. This is what is called a fully developed flow. Okay. This is what is called a fully developed flow. The fact that the flow is unidirectional implies that it is fully developed. Okay. That is because there is no velocity u y, it is necessary that partial u x by partial x has to be equal to 0. Okay. Now, that has implications for the x momentum conservation equation. Okay. Because the flow is fully developed, this term is equal to 0. Okay. U x partial u x by partial x is identically equal to 0 because u x is independent of x. Similarly, this term is 0 because u y is equal to 0. Okay, this term is 0 because u y is equal to 0. And finally, this term is equal to 0 because partial u x by partial x is equal to 0. Okay. So, for a fully developed fluid, okay, another important implication, since partial p by partial y is equal to 0, right, partial p by partial x is independent of y. Okay. So, this pressure gradient term, okay, since the pressure itself is independent of y, pressure itself is independent of the cross stream direction, that means that the pressure gradient is also independent of y. Independent of y. The pressure itself is also independent of y. Therefore, my x momentum conservation equation reduces to rho partial u x by partial t is equal to minus partial p by partial x plus mu partial square u x by partial y square for this simple one dimensional flow. Okay. So, this is the equation for a fully developed flow. Okay. In addition, if the flow is steady, steady means time independent. If the flow is fully developed and it is steady, that means that this term is also equal to 0. Okay. So, for a fully developed steady flow, minus partial p by partial x plus mu partial square u x by partial y square is equal to 0. And if you recall, these were the exact equations we had for unidirectional flows for a fully developed steady flow with partial p by partial x being independent of y. Okay. So, this is the equation, it is quite easy to solve it. Okay. For definiteness, let us take two boundaries at y is equal to 0 and y is equal to h. Okay. The two boundaries of this slot are at y is equal to 0 and y is equal to h. You require the no slip condition at those two surfaces. The velocity has to be equal to 0 at y is equal to 0 and y is equal to h. And on this basis, you can quite easily solve the equations to get the exact velocity profile. Okay. The resulting solution that you will get for the velocity profile is u x is equal to minus h square by 2 mu partial p by partial x into y by h into 1 minus y by h, quadratic solution for the velocity profile. Okay. there is a maximum value of the velocity at y is equal to h by 2. Okay, the velocity is a maximum at the center of the channel. Okay, the velocity is maximum exactly at the center of the channel h by 2. Okay, and that maximum component velocity is given by ux max is equal to minus partial p by partial x into h squared by 8 mu. Okay. And therefore, ux is equal to 4 ux max into y by h into 1 minus y by h. Okay. And you can easily calculate the average velocity by integrating across the cross section and dividing by total h, and you will find that u average in the x direction is equal to 2 by 3 of the maximum velocity. Is equal to 2 by 3 of the maximum velocity. Okay. And on that basis, you can calculate the friction factor. Okay. The friction factor F for this flow is defined as minus delta p by delta x by rho u square average square by 2 h, okay, which is end up giving you 24 by the Reynolds number. Okay. So, this once you know that for a unidirectional flow the equation has to be of this form, okay, then it is quite easy to solve. Okay, you just get a quadratic equation, because from the two equations we know that the pressure is independent of y as well, okay, and then we can solve to get the two equations. If the flow is fully developed but not steady, the equation that you get is this one. Okay. If the flow is fully developed but not steady, you have the time derivative as well. That, if you recall, we had done in detail in Fundamentals of Transport Processes 1, where I showed you how you get boundary layer solutions in the limit where the inertial terms are dominating. Okay, in that limit, you will get boundary layer solutions at the wall, and the flow near the center will be a plug flow. Okay, if you recall, we had done that in detail in the Fundamentals of Transport Processes. In that case, the flow is fully developed, no variation in x, but it is not steady. It depends upon time. That is because the pressure difference applied across the two ends is time dependent. One can have such a situation where the pressure is time dependent, but the velocity is not, because pressure travels at the speed of sound. Okay. So, pressure equalizes instantly across the entire width of the pipe at the speed of sound, whereas the velocity in the pipe is usually much slower. So, in many cases it is a good approximation to consider that the pressure is instantaneously changing its value, the pressure gradient everywhere is instantaneously changing its value, and the response time of the velocity is much smaller. So, you solve for the time dependent velocity profile, assuming that the pressure gradient everywhere is a constant independent of position, but dependent upon time. Now, a similar thing can be done for a pipe flow. Okay. For a pipe flow, you can do a similar thing. Okay, let us say you have a pipe with radius r, okay, and you have a pressure difference across, which drives a velocity across the pipe. Okay, you can do a similar thing for a pipe flow. Okay. I will not go through the details of the calculation. In this particular case, we will assume a coordinate system where x is the streamwise coordinate and r is the radial coordinate. Okay, so, you have an r x coordinate system. R is the distance from the axis, cylindrical coordinate system, x is along the axis, phi is the angle around, the meridional angle. If we assume that the flow is axisymmetric, there is no variation with phi, okay. There is a variation only with r and x. If the flow is unidirectional, there is no variation of the velocity, okay. There is no variation of, I am sorry, if the flow is unidirectional, there is a velocity only in the x direction, no velocity in the r direction. Mass conservation equation in cylindrical coordinates, 1 by r d by dr of r partial u r by partial r plus partial u x by partial x is equal to 0. The divergence in a cylindrical coordinate system. Once again, if the flow is unidirectional, partial u x by partial x is equal to 0. So, once again u x cannot be dependent upon x, and therefore, one has simply a fully developed flow. Unidirectional implies fully developed. Next, the momentum conservation equation in the x direction. Okay, the momentum conservation equation in the x direction. Once again, rho partial u I by partial t plus u j partial u I by partial x j is equal to minus partial p by partial x I plus mu del square u I. Del square is a Laplacian operator, which will be different now in a cylindrical coordinate system. Momentum conservation in the x direction, that means I is equal to x. So, you will get rho into partial u x by partial t plus u x partial u x by partial x plus times the Laplacian operator acting on the x velocity. Similarly, for the r direction, exact same momentum conservation equation for the r direction. Similarly, for the r direction. In the r equation, flow is unidirectional, okay, flow is unidirectional. Therefore, I just get minus partial p by partial r is equal to 0. It's simple for a unidirectional flow. Okay. In the x momentum conservation equation, okay, this term is 0 because partial u x by partial x is equal to 0, fully developed flow. Okay. This term is 0 because there is no variation, there is no velocity in the r direction. Okay. So, in the r direction there is no velocity, and therefore, that term is equal to 0. This is equal to 0 because the flow is fully developed. Okay. The flow is fully developed. So, this is equal to 0, and also since pressure is independent of r, dP by dx is also a constant, it is independent of r. Okay. It is independent of r. Okay. dP by dx is also independent of r. Therefore, the equation that I get is will be of the form rho times partial u x by partial t is equal to minus partial p by partial x plus mu 1 by r d by dr of r partial u x by partial r. Now, p is independent of r, and therefore, dP dx is also independent of r. A fundamental doubt that is often raised is, does this thing dP by dx, does it have to be a constant, or can it depend upon x itself? Okay, is dP by dx, does it have to be a constant, or can it vary with x? In other words, is the pressure have to be a linear function of x, or can it be some other complicated function of x? The answer is quite simple. The way you can resolve that is just by taking the derivative of this entire equation with respect to x. Okay. So, I take this entire equation and I take d by dx of that, and you know that you can interchange the order of differentiation. The differentiation with t can be interchanged with the differentiation with x. Similarly, the differentiation with r can be interchanged with the differentiation with x, because they are both independent variables. Okay. So, therefore, the equation that I get will be rho into partial by partial t of partial u x by partial x minus d by dx of dp by dx plus mu 1 by r d by dr of r d by dr of partial u x by partial x. Okay. This took the derivative with respect to x, and it interchanged the order of integration and interchanged the order of differentiation with respect to t and r and with respect to x and r. Now, for a fully developed flow, partial u x by partial x is equal to 0. That means that these two terms are both equal to 0, okay, because partial u x by partial x is equal to 0, because unidirectional implies fully developed. Therefore, d by dx of dp by dx is equal to 0. We already know that p is independent of r, okay, and this shows that the second derivative of p with respect to x has to be equal to 0. That means that p has to be a linear function of x, or dp by dx has to be a constant. Okay. So, that is why the pressure gradient will always be a constant for a unidirectional fully developed flow. Okay. So, that is the reason why it is always assumed that this pressure gradient is a constant. Okay. So, this is for a fully developed unidirectional flow. If it is also steady, the time derivative is equal to 0, and I get my simplified equation as minus partial p by partial x plus mu into 1 by r d by dr of r partial u x by partial r, okay, that is equal to 0. And you can easily solve for the conservation equation to get the velocity profile. Okay. You get the well known solutions. U x is equal to minus r square by 4 mu partial p by partial x into 1 minus r square by r square. These are obtained using the boundary conditions that the velocity is equal to 0 at r is equal to capital R. Okay. And for the flow in a pipe, the maximum velocity u x max is equal to minus r square by 4 mu dp by dx. U average is equal to the maximum by 2. Okay. And the friction factor, which is defined as minus partial p by partial x by rho u average square by 2 d, okay, where d is the diameter of the pipe, okay, is equal to 64 by Reynolds number. Okay. This is defined based upon the diameter. The rho u square average square by 2 is the kinetic energy, and you divide by the diameter. Okay. The other way is to express it in terms of the hydraulic radius. The hydraulic radius is d by 4. Okay. So, the other friction factor is minus partial p by partial x by 2 rho u average square by d is equal to 16 by r e. Okay. So, it is defined with the radius as the length as the characteristic length in one case, the Darcy friction factor, whereas the fanning friction factor is usually defined with the hydraulic radius, which is the diameter divided by 4. Okay. So, this gives you the friction factor for the flow in a pipe. Okay. In the case of an unsteady flow, of course, you just include the time derivative in the equation as well, and one can get boundary layer solutions similar to what we had done in fundamentals of transport processes 1. Finally, let us just look at one particular case where we actually have a flow being driven by the body force. Okay. Well, let us look at one case where the flow is being driven by a body force. Okay. That is flow down inclined plane. I have a fluid of height h, okay, coming down an inclined plane in which the gravity vector is acting in this direction. Okay. And of course, since the flow is coming at an angle, okay, this angle is theta, okay, and I put my coordinate system x and y to be along with and perpendicular to the plane itself. Okay, I put my coordinates to be along and perpendicular to the plane itself. Those are the flow directions and the cross stream directions. We assume that the the length is sufficiently long that it has reached a fully developed flow, in which case my mass conservation equation partial ux by partial x plus is equal to 0. If it is a unidirectional flow, then uy is equal to 0, and therefore, I just get ux is independent of x. Okay. Now, in my momentum conservation equations for the x and y directions, then I have a body force here. Body force is proportional to the component of the gravity, acceleration due to gravity, which acts along the x direction. So, g x is equal to g times sin theta, the component of the gravitational acceleration, which is acting along the flow direction. Okay. Then I have the cross stream velocity. Plus rho times g y. There is a mistake here, and that is that both of these have to be y, and this one also has to be y. As usual, all terms in the y momentum conservation equation will end up being which are proportional to the velocity will end up being 0, because uy is equal to 0, and therefore, the y momentum conservation equation just reduces to minus partial p by partial y plus rho g y is equal to 0. So, the y momentum conservation minus partial p by partial y plus rho times g y is equal to 0, where g y is equal to minus, okay, g y is pointing downward. So, g y is equal to minus g cos theta, okay, but we will just assume it is a constant here. Okay. This can be solved easily, okay, to give me a solution. P is equal to P naught plus rho g y times y. Okay, just integrate this once. Okay. P is equal to P naught plus rho g y times y. Okay. This P naught in general, okay, is the value of the pressure at y is equal to 0. This P naught is the value of the pressure at y is equal to 0. When I do the integration, I am integrating a partial differential equation with respect to y. So, the constant of integration that appears can in general be a function of x. That constant of integration can in general be a function of x, because I am integrating with respect to y. So, in this expression, if I take the derivative with respect to y, keeping x a constant, I just get rho times g y. Okay, that satisfies the differential equation. How do we know what the value of P naught is? Okay. How do we know what the value of P naught is? We know that at the top interface, this liquid is in contact with a gas, and therefore, the pressure at that top interface has to be a constant. Okay. The pressure at the top interface has to be equal to the pressure in the gas, okay, because this is a free moving interface of fluid flowing down an inclined plane, which is in contact with the atmosphere. Okay. So, the pressure at that top surface has to be equal to atmospheric pressure itself. Okay. That means that at y is equal to h, okay, at y is equal to h, P is equal to P atmosphere. Okay. So, this pressure, this constant can be determined from the boundary condition, normal stress condition at y is equal to h, P is equal to P A. That means that P naught of x is equal to P atmosphere minus rho G y h. Okay, because at y is equal to h, P is to be equal to P atmosphere. That means that the constant of integration which was dependent upon x from the boundary condition, since P atmospheric is independent of x coordinate, that means that P naught also has to be independent of the x coordinate. Okay. Because the pressure has to be atmospheric pressure at that top surface. Okay. An important implication of this is that partial P naught by partial x is equal to 0. That means that P naught is independent of x, and also the pressure itself, okay, because P is equal to P naught plus rho G y y. So, if the pressure P naught is independent of x, that means that P is also independent of x. The implication is that the pressure is also independent of x. Therefore, this term here is equal to 0. That comes from the free interface condition and from using the y momentum conservation equation. Okay. So, this has given us an important fact which we can use in the x momentum conservation equation. Of course, for a unidirectional flow, there are terms in this x momentum conservation equation which will all go to 0. Okay. For example, because u x is independent of x, this term is going to go to 0. Because u y is independent of y, I am sorry, u y is equal to 0, this term is equal to 0, and this second derivative is also going to be equal to 0. Okay. So, finally, I will end up with solving the equation rho partial u x by partial t is equal to mu times partial square u x by partial y square plus rho times g x. So, this is for a fully developed unidirectional flow down an inclined plane. Okay. If it is also steady, that means that my equation just becomes mu partial square u x by partial y square plus rho g x is equal to 0, okay, for a steady fully developed flow. Okay. I can solve this equation. U x is equal to minus rho g x by mu into C naught plus C 1 y, okay, where the constants C naught and C 1 have to be determined from the boundary conditions. So, I am sorry. Y square by 2 plus C naught plus C 1 y, okay, where C naught and C 1 have to be determined from the boundary conditions. Okay. The boundary conditions are at this bottom surface, I have the no slip condition, that means the velocity is equal to 0 at that surface. Okay. So, at y is equal to 0, right, u x is equal to 0, and at the top surface at y is equal to h, okay, the liquid is in contact with the gas. At y is equal to h, the liquid in contact with the gas. Therefore, the appropriate boundary condition to apply is that the shear stress is equal to 0. The appropriate boundary condition is that the shear stress at that surface partial u x by partial y is equal to 0. which means that partial u x with respect to y is equal to 0. Okay. So, using these two boundary conditions, one can determine the two constants in the equation, okay, to get the velocity field u x is equal to rho g x by mu into h square by mu into y by h minus y square by 2 h square. This is a parabolic profile which has the maximum velocity at y is equal to h. Okay, at y is equal to h, this becomes equal to u x max is equal to rho g x h square by 2 mu. The average velocity will be half of this. Okay, so, the velocity profile that I will get for the flow down an inclined plane is something that looks like this. Okay, parabolic velocity profile for which the slope becomes 0 as the top interface is approached. Now, this profile for flow down an inclined plane is also a very useful one to discuss one of the other issues that we have not discussed so far, and that is what happens at a liquid interface. Okay. So, I have a flow down inclined plane. At an angle theta, but rather than having just one liquid flowing down the inclined plane, I have two layers of liquids flowing down the inclined plane. Okay. This is x, this is y. I have two liquids A and B that are flowing down the inclined plane. Okay. So, I have liquid A with height h A, and I have a second liquid B of height h. Okay. So, so, I have one liquid for which y is equal to h A at the interface, and the other liquid for which y is equal to h B. So, I have two liquids with two different viscosities, mu A here mu A here and mu B here. Okay. So, I will assume for simplicity that the densities of these two are the same, only the viscosities are different. It is quite easy to extend this to the case where both the densities and the viscosities are changing. Okay. So, for the two fluids, okay, I have my equations are mu A partial square u x A by partial y square is equal to minus rho g x. Okay. It should be rho A g x, but I assume that the densities are both the same. Okay. And therefore, for this liquid A, I have this relationship, whereas for the liquid B, my relationship becomes mu B times partial square u x B by partial y square is equal to minus rho g x. Okay. The solutions are u x A is equal to minus rho g x y square by 2 mu A plus one constant A times y plus B A, and u x B is equal to minus rho g x y square by 2 mu B plus constant y plus another constant. So, now there are four constants. Okay. That means that I need 4 conditions to completely specify all 4 of these constants. Okay. Boundary conditions. There are 2 boundaries, one at y is equal to 0, which is the boundary between the bottom fluid and the solid surface. The other at y is equal to HB, boundary between the top liquid and the gas, and there is an interface between these two. So, at the bottom boundary I require that at y is equal to 0, ux a is equal to 0. Okay. At the top surface at y is equal to h b, okay, the shear stress has to be equal to 0. Okay. That is mu b times partial ux b by partial y has to be equal to 0. Okay. And then I have the interface conditions. At the interface between the two liquids, the velocity has to be the same and the stress has to be the same. Okay. There is no normal velocity, so there is no need to enforce a velocity condition in the y direction. The only velocity condition that has to be imposed is in the x direction. There is no normal, the normal stress is only due to pressure. So, basically the normal stress condition will basically tell you that the pressure in both liquids is same as the interface. The shear stress condition basically is that the velocity A, okay, at y is equal to h a. Velocity A times partial ux a by partial y is equal to the velocity, I am sorry, the viscosity in B times partial ux b by partial y. Okay. That is the continuity of stress condition, and there is a continuity of velocity condition ux a is equal to ux b. So, these put together basically give you 4 equations with which you can find out what the values of the 4 constants are. Okay. Okay. It basically gives you 4 equations which you can use to find out what the values of the 4 constants are. Okay. So, in this particular case I am going to enforce the the equality of velocity as well as the equality of stress in both fluids, and from that I will find out what all 4 constants are. Okay. So, at y is equal to 0, ux a is equal to 0, that will imply that the constant B a is equal to 0. Okay. At y is equal to h b, the derivative is equal to 0. That means that minus rho g x h by mu b plus a b is equal to 0. Okay. So, these give you 2 of the constants, B a is equal to 0 and A b is equal to rho g x h by mu b, because the shear stress at the top interface is equal to 0. Okay. And from these 2 equations I will get the 2 more constants. Okay. It's just an exercise in algebra, so I will not go through the details. From these 2 equations I will get the other 2 constants, and these constants turn out to be A okay, is equal to rho g x into h a into 1 by mu a minus 1 by mu b plus h b by mu b, and b is equal to rho g x h a square by 2 into 1 by mu a minus 1 by mu b. So, that completely fixes all 4 constants in the equations. Okay. Now, these both are quadratic equation, these are both parabolic velocity profiles. Okay. Both of these are parabolic velocity profiles, and therefore, the kind of profile that you will get here is something that will look like this. There will be a change in the slope at that point, okay, because even though the shear stresses are equal, okay, even though the shear stresses, as you can see, the shear stresses on both sides are equal, the viscosities are not equal. That means that there will be the derivatives of the velocity at the interface will not be equal. you will get a different slope in one liquid as compared to the other liquid. Okay. So, there will be a discontinuity in the slope of the velocity at that point, the derivative of the velocity, and that discontinuity will of course depend upon which liquid is more viscous. Okay. The liquid which is more viscous will have the lower derivative, because the stresses are equal, viscosity is higher, the derivative is lower. Okay. So, if the liquid is for example more viscous, the derivative here will be lower, then you will have a higher derivative in this second fluid. If it is the other way around, you will get something that looks like this with the lower derivative on top. Okay. In either case, the slope right at the top has to be equal to 0, because the shear stress is equal to 0. At the bottom, the velocity is 0. You have two conditions in between, and you have 4 constants. So, you can solve all of these 4 to get the velocity profile for an interface problem. So, this completes our discussion on unidirectional flows. Okay. I just shown you how you can quite easily from the equations recover all of the results that we had got in the fundamentals of transport processes 1 based upon shell balances. Now, let us look at the equations for a general velocity profile. Okay. The equations are partial u I by partial x I is equal to 0, and rho times partial u I by partial t plus u j partial u I by partial x j. So, these are the mass and momentum conservation equations, the Navier-Stokes equations. And let us take a general problem, we will not specify it too closely, too clearly at this stage, in which we have a characteristic velocity scale u and a characteristic length scale L. Okay. So, I have characteristic velocity u. Okay. So, therefore, I can define a scaled coordinate as x I by L and a scaled velocity as u I by u. The scaled time is quite easy to get, because from a velocity scale u and a length scale L, the only way you can get a time scale is to define T I star is equal to T I times u by L, I am sorry, T star. Is equal to T times u by L. Okay. So, that is the characteristic time scale. Okay. Let us express this equation in terms of those characteristic length and velocity scales. Okay. So, the mass conservation equation just becomes u by L partial u I by partial x I is equal to 0. Okay. And of course, I can cancel out that u by L to just get the mass conservation equation as partial u I by partial x I equal to 0. So, that is the mass conservation equation. Momentum conservation equation, on the left hand side I have velocity square divided by length. Okay. I have velocity square divided by length. Therefore, if I take out that express this in terms of the scaled variable, one can easily verify that you will get rho u square by L partial u I by partial t plus the pressure we have not scaled yet, we will come back to that. Okay. So, is equal to minus 1 by L partial p by partial x I plus the viscous term mu times velocity square divided, I am sorry, mu times velocity divided by length square. Okay. So, this becomes mu u by L square partial square u I by partial x j square. Okay. Now, these velocity and length scales are characteristic to the particular problem. Okay. For example, if I had a sphere of diameter d dropping with a velocity u in a liquid or in a fluid, a sphere of diameter d with a velocity u, characteristic length is d, characteristic velocity is u. Okay. On the other hand, if I had a pipe flow, okay, pipe of diameter d with maximum velocity u, then the characteristic diameter is d, characteristic length L is d, and velocity is u. Okay. Similarly, you could have more complicated cases, but in all those cases you will have something, either the motion of an object within the fluid or the motion of the fluid itself, which will give you a characteristic velocity scale, and there will be some characteristic length scale, either set by an immersed object or set by the boundaries in flows through confined geometries. Okay. So, those are the characteristic length and velocity scales in this case. Now, this momentum conservation equation I can non-dimensionalize in two ways. Okay. You can non-dimensionalize either by dividing by the coefficient of the inertial terms, which are proportional to the density u square by L, or by dividing by the coefficient of the viscous terms mu u by L square. Okay. Which you choose will depend upon what you expect to be the dominant force in this problem. Okay. If you expect the dominant force to be viscous, you divide throughout by mu u by L square. Whereas, if you expect the dominant force to be inertial, you will divide by rho u square by L. Okay. So, let us take the viscous scaling. Okay. We expect the viscous force to be dominant. Okay. If we take the viscous scaling, divide throughout by mu u by L square, what I get is rho u L by mu minus partial p star by partial x I star plus mu, I am sorry, okay, where my scaled pressure p star is equal to p by mu u by L. Okay. So, this gives me a dimensionless number here. Okay. So, this, as you all know, is the familiar Reynolds number. Okay. R e times the inertial terms is equal to minus the pressure gradient plus the viscous terms in the conservation equation. Okay. On the other hand, if I choose to scale it by the inertial terms, if I divide throughout by rho u square by L, this you would do when you expect the inertial forces to be the dominant forces. If you expect the inertial forces to dominate, the viscous forces to be negligible, then you would scale by the inertial terms in the conservation equation. In that case, the equation that I would get is partial u I by partial t plus u j partial u I by partial x j minus partial p. I will call that as an inertially scaled pressure with 2 stars plus 1 by R e partial square u I by partial x j square, okay, where p star star is an inertial pressure p by rho u square. Okay. So, the first equation you would use when you expect the viscous forces to be dominant. I have a Reynolds number times the inertial forces equal to minus pressure gradient plus viscous forces. The next you would use when you expect inertial forces to be dominant, so that you would expect a balance between the inertial forces in the equation and the pressure gradient. Okay. In the first case, if the viscous forces are dominant, viscous force is the ratio, I am sorry, the Reynolds number is the ratio of inertia by viscosity is equal to rho u L by mu. It is the ratio of the inertial and the viscous forces. Okay. If I expect the viscous forces to be dominant, the Reynolds number will be small. You would expect that there would be a balance between the pressure gradient and the viscous forces, and the inertial terms can be neglected. The diffusion dominated regime. Okay. This Reynolds number can also be written as u L by the kinematic viscosity. Okay. The kinematic viscosity is the momentum diffusivity. On the other hand, if the Reynolds number is large, you would expect that the inertial forces are dominant. I have a 1 over R e here multiplying the viscous term. So, when R e is large, 1 over R e is small, and I would expect I could neglect the viscous terms and only solve for the inertial terms in the conservation equation. Balance the inertial terms with the pressure gradient. Okay. So, that is the inertia dominated regime, high Reynolds number regime. Okay. However, as we saw in our previous encounter with convection dominated transport, even when the Reynolds number is large or the Peclet number is large, you would think that you can neglect diffusion in comparison to convection. However, when you neglect diffusion, the equation transforms from a second order differential equation to a first order differential equation, and you cannot satisfy all boundary conditions. Physically, you cannot satisfy boundary conditions because at the boundaries, the transport that takes place is only if you neglect diffusion, there is transport only due to convection, and convective transport can take place only along the flow direction. To transport mass, momentum or energy from or to a bounding surface, you need transport that is perpendicular to the bounding surfaces. That transport can happen only due to diffusion. In the case of fluid mechanics, it is a little more complicated than that, because in general I could have a balance between inertial and pressure forces as well. Okay. So, I do get non-trivial solutions when I balance inertial and pressure forces, okay. And in those cases I cannot satisfy tangential velocity boundary conditions. Okay. However, if I want to satisfy tangential velocity boundary conditions, I have to once again postulate a thin boundary layer at the surface where inertial and viscous forces are balanced. The thickness of the boundary layer is determined on the basis of the condition that for that small thickness there is a balance when because the thickness is small, the gradients are large, and when the gradients are large, there is once again a balance between inertial and viscous forces in this limit. So, that is going to be our strategy for looking at fluid mechanics problems. Okay. We look at special cases. The first is low Reynolds number. Okay. In this case, you neglect inertia. Okay. And my conservation equation in the absence of the inertial terms, that you set the density is equal to 0, and I just get 0 is equal to minus grad p plus mu times partial square u I by partial x j square, and the divergence of the velocity. The divergence of the velocity is also equal to 0. So, that is the first case, low Reynolds number. In the case of momentum, mass and energy transfer, I just had this term. In the case of mass and energy transfer, I just had this term. For momentum transfer, I also have a pressure, and for solving that pressure, I have the incompressibility condition. Okay. The second case is high Reynolds number potential flow. Okay. In this case, you have just the balance between the inertial terms and the pressure gradient and the incompressibility condition. In this case, one can no longer satisfy the tangential velocity boundary conditions for the velocity of the stress, because I have neglected the highest derivative. Okay. And then the third step will be to include that very near boundaries, because I realize that transport to boundaries has to take place only due to diffusion, and that is boundary layer theory. So, this is the broad strategy on the basis of which we will analyze fluid flows from the Navier-Stokes equations. Next lecture, we start with low Reynolds number flows. So, we will see you in the next lecture. Continue, we will start low Reynolds number fluid mechanics in the next lecture. Kindly revise the conservation equations that we have done here, so that we can start next lecture on viscous flows in the absence of inertia. We will see you next time.